A particular kind of application that we see with systems of equations is one dealing with a network. And in a network, we have pretty much a closed system. In this case, we have roundabouts in England, and there are a lot of these one-way streets. So we can see where traffic is flowing. And typically this will be over the course of some fixed period of time, say over an hour or a day. And perhaps we have ways of keeping track of how many cars are flowing in and out. We've all seen those cables across streets where what they're doing is they're counting the number of cars, but they don't do it everywhere. It gets expensive, a lot of equipment and maintenance, and people have to lay them out. So they put them in strategic places often. And maybe we want to resolve some of the other regions, say between these intersections, which we could think of as A, B, C, D, E, and F. Assume the traffic must travel in the direction shown. Find the general solution of the network flow. So in other words, we want to know, based upon the fact that 60 cars are coming into what we'll call intersection A, and 100 more cars are entering into intersection C, and then we can see how many are, as well as 80 into E here. We want to be able to figure out what these other components are as best we can, if it's possible. So we have to figure out, well, how are we even going to construct equations for this? And what we want to do is we want to draw our attention to these nodes. In this case, these would be intersections. And we know something about the intersections. The biggest assumption that we can draw here is that the number of vehicles entering into a given node has to equal the number of cars exiting that node. Right? So in this case, if we focus on intersection A, and x1 through x6 are defined to be the number of vehicles in that particular region or driving across that particular region, then we know for intersection A, the number of cars in, and I'll just write this general relationship, cars in equals cars out. And that's key in developing our equations. So into intersection A, we have 60 cars coming in, but then notice that we also have cars coming in from intersection F. How many that is, well, we don't know the exact number, but we know it's x6. So we could say that the 60 cars coming in plus the x6 cars coming in has to equal the number of cars going out. We'll notice that this arrow actually points outwards, and there are x1 cars leaving intersection A. So there's our first equation. The number of total cars in has to equal the number of total cars out. Now we'll repeat the same thing for each of those intersections. So for B, how many do we have coming in? Well, the only arrow pointing into B is x1. So we have x1 cars coming in, and the total cars going out is going to equal 70 plus the x2. So the number of cars coming in has to equal the number of cars coming out. In this case, they split off into two different directions. So this is going to be 70 plus x2. For intersection C, again, we have two sources coming in, 100 and x2. If we add the number of cars coming in total at intersection C, that has to equal the number of cars going out, which is equal to x3. For intersection D, repeat this. So cars coming in would be only x3. Cars going out would be 90 plus the x4. Intersection E is going to be x4 coming in, 80 coming in, so 80 plus x4. And that has to equal the number of cars going out, which is x5. And then finally, we have intersection F here. In intersection F, we have only x5 cars coming in. And then going out, that splits between the ones that are exiting left out of the network or out of the roundabout, and then the x6 that are continuing along the roundabout. And that will be 80 plus x6. Okay, now we don't need to worry about the the total number of cars entering the network, because if you notice, if you take 100 plus 80 plus 60, 100 plus 80 plus 60 is 240. and then going out is also 240. So that just means that we have 240 cars coming in that given time and 240 cars going out at that given time. That's not going to be a very useful equation. So we just really need to target those nodes in that network. And so now in order to resolve what x1 through x6 should be, we need to rearrange these equations, and we can do this in a couple of different ways. We just need to make sure we get our variables on the left and our constants on the right. So I suppose I'll just go ahead and subtract x1 over, giving me negative x1 plus x6. And then I guess I have to move the 60 over to the other side. You could alternatively just subtract x6 and make this x1 minus x6 equals positive 60. You'll notice that's exactly the same equation. It's just both sides multiplied by a negative 1. And here I suppose I'll move the x2 over. x1 minus x2 equals 70. Here I think I'll just move the x2 over, the x3 over, and then subtract the 100 over the other side. Here I'll move the x4, making this x3 minus x4 equals 90. Here I think I'll subtract over the x5, and then I'll subtract over the 80. Finally, here I'll just subtract the x6 from both sides, leaving me with x5 minus x6 equals 80. So this should be my system of equations right here that I'm going to now convert into matrix form. So just double checking, make sure we have this all set up correctly, no mistakes. Again, a number of different ways you can subtract things over. It's an equation, so as long as you do the same thing to both sides, this could be, for example, negative x2 plus x3 equals positive 100. That would be totally fine as well. So I'm going to set up a matrix here, and I'm just going to be really careful because I'm going to have a lot of columns here. I'm going to have 1, 2, 3, 4, 5, 6 rows. So I'm going to make enough room for that. And I'm going to go ahead and just label the columns just for my own visual sake, because one of the things that we can do in modeling, as far as making mistakes, is misinputting things into our matrix. So I'm going to start with the constants here. I'll have negative 60, 70, negative 100, 90, negative 80, and positive 80. And for the first row, we have just a negative x1, so a negative 1 x1 plus 1 x6. So I'm just going to put a negative 1 here and a positive 1 here, and then fill the remaining zeros, because I don't have any x2 through x5s. Here I just have 1 x1, negative 1 x2. 1, negative 1, 0, 0, 0, 0. There's going to be a lot of zeros in this matrix. Here I have a 1x2 minus 1x3. So I'll have 1, negative 1. Zeros everywhere else. For the 90, I'll have 1x3 minus 1x4. Zeros for all of the other 4 variables. And almost there. So here I have 1x4 minus 1x5. So I'll have a 1, negative 1, and zeros everywhere else. Finally, 1x5 minus 1x6. Get that negative sign there, 1, 2, 3, 4 zeros. You kind of notice that it has like these negative ones along one of the diagonals and then a 1 there. That's sort of because of the roundabout nature, no pun intended, of our network here. And so now we're prepared to do some elimination. So if I dump this into a calculator, here is what we get when we use our preferred source of technology. And the first thing we should point out as far as solutions are concerned is when we take a good look at this, we can see in the bottom row we have a row of zeros. And this is effectively not helpful at all, except that it doesn't result in a no solution situation, which we would get if we had all 0 coefficients, but a non-zero constant. Also, the other thing we should point out is that we see that if we go row by row, that we can figure out where our non-zero pivot is. So we see that we have a non-zero pivot in row 1 for x1, which makes x1 a non-free variable. x2, we see that has a pivot in the second row. x3 in the third row. x4 in the fourth row. x5 in the fifth row. And then the sixth row doesn't have a non-zero pivot, so that means that x6 is free. Also, an easy way to deduce that logically is that every single one of these equations, these first 5 equations, is x1 minus x6 equals 60, x2 minus x6 equals negative 10, x3 minus x6 equals 90, x4 minus x6 equals 0, and x5 minus x6 equals 80. And so we see that each of them depends upon the value of x6, but there is no guidance for what x6 should be. So we will say let x6 equal some constant. So some real number. I won't write that out, but that's usually what we say. And therefore, that would mean that x1, I write this in vector form. So x6, we just said, hey, that could be anything we want to assign it to, or assign to it. Of course, we're going to have to think about the practical implications of what we're writing here, but we'll look at that in a moment. x1 will be 60 plus x6, because if x1 minus x6 equals 60, then moving the x6 to the other side, well, x6 is equal to constant, so 60 plus c will be this value. The next one will be negative 10 plus c. x3 will be 90 plus c. x4 will be c, right? Because we'll move that over to the other side. 0 plus c, which is just c. And here x5 equals 80 plus c. So what this means in the context of this network is that we have a free variable, meaning that without knowing the value of x6, we can't fully determine what x1 through x5 are. So in the practical scheme of things, there's not enough information to be able to know for sure what all of these intersections are, or what the flow along each of these segments between intersections is. But the question is, find the smallest possible value for x6. Well, we might say that at first that should be 0, right? Because, okay, we could have 0 vehicles flowing in that region. But the problem with that is that if c equals 0, then check this out. Well, x1 would be 60. x2 is where we get our problem, because negative 10 plus 0 is negative 10, and that just can't be, right? You can't have negative vehicles flowing along, and you can't say it's in the opposite direction because these are all one way. So in order to avoid, and this is really our target right here, this is where our minimum must be, we must carefully select it. Now notice that the other ones are adding c to it. So as long as c is not negative, then there's no chance that x1, x3, x4, x5, and x6 are in any way negative. In order for x2 to be a valid number, we know that x2 has to be greater than or equal to 0. Okay, x2 can be 0, it just can't be negative. Well, what is x2? It's negative 10 plus c must be greater than or equal to 0. And so that means c must be greater than or equal to 10. Now, the question was about x6, right? What's the smallest that x6 can be? Well, x6 is c, so that means x6 has to be at least 10 vehicles. That answers our questions. This is a problem where we have to construct a model, involves a lot of variables. We have to be very careful about entering this into a matrix form. And then when we found our solution, we had to really think about the practical implications of what's going on.